So today we will see one problem, example problem on the axial vibration of rod. Okay, axial vibration of rod. Okay, so this is what the problem says. Find the natural frequency of axial bar of uniform cross section of 20 millimeter square. Length is given as 1 meter. Young's modulus is given as 2 into 10 raised to 5 megapascal, that is Newton per millimeter square. Okay, and density is given as 8000 kg per meter cube, and they have also specified as take two linear elements. Okay, take two linear elements, and they haven't given any diagram. Okay, diagram is not required when they are saying two linear elements. Okay, the arrangement can be done in this manner. Okay, and since they are saying it is axial bar or only uniform cross section bar, okay, so we know that bar element, okay, bar element, the one end is fixed, okay, one end is fixed and the other end is open, and we are trying to identify the axial vibrations. Okay, axial vibrations, and vibrations thereby we mean the natural frequencies for axial vibrations. Okay, so if I have, let's say, two elements, okay, two elements if I am considering, okay, then I would probably have, let's say, a matrix order of 3 by 3, okay, 3 by 3, and which is the global matrix order, okay, global stiffness matrix order along with the mass matrix order. Okay, and since they haven't specified anything about which type of mass matrix to be used, okay, remember we have two types of mass matrices. One is consistent mass matrix and the other is lumped mass matrix. Okay, so they haven't specified anything. If in a problem there is no specific mass condition is given, then by default we will be using consistent mass matrix. Okay, by default we will be using consistent mass matrix. Here also we will be using consistent mass matrix. Okay, the problem can also be asked in a fashion wherein they would ask you to find both the values, okay, that is the frequency value by considering consistent mass, frequency value by considering lumped mass. Okay, so that can also be done. Okay, that can also be done. So let us get started. Okay, we know that since they have asked us to use two linear elements, so it would be two linear elements, okay, joined together in this manner. So I have an axial bar. Okay, I have converted them into two linear elements. So I will have node number 1, node number 2, node number 3. By default, node number 1 will be fixed. Okay, node number 1 will be fixed. Since this is one dimensional element, I know displacements are u1, u2, u3. So u1 is equal to 0. That is my boundary condition. Okay, so let's write the element matrix equation for the vibration problem. So it is AE by L 1 minus 1 minus 1 1 multiplied by the displacement vector matrix, which is u1 u2, is equal to omega square rho a L by 6. Okay, omega square rho a L by 6 2 1 1 2 multiplied by displacement vector matrix u1 u2. Okay, now we had seen this equation, that is element matrix equation, and we have also seen the derivation of the same. Okay, so now what we will do, we are going to use this equation, put all the values in the equation. Okay, the only unknown value happens to be omega square. Okay, only unknown value happens to be omega square, and since omega square term is coming, so we will be ideally having two values of omega. Now omega is what? Omega is natural frequency with which the axial rod is going to vibrate. Okay, axial rod is going to vibrate, and we are just trying to identify that natural frequency by this finite element method. Okay, so I'll put all the values. Okay, area of cross section 20 millimeter square. Okay, Young's modulus is 2 into 10 raised to 8. Length is 1 meter. So since everything is given, let's say the unit of length, let us keep it as meters. Okay, unit of length, let us keep it as meters, so that we don't have to convert this density also. This can be easily rewritten in terms of Newton per meter square as 2 into 10 raised to 9. Okay, 2 into 10 raised to 11 or 200 into 10 raised to 9. Okay, so that we will do 2 into 10 raised to 9. Okay, L I have 1, okay, and cross section is millimeter square, so I can easily rewrite it as 20 into 10 raised to minus 6, okay, 20 into 10 raised to minus 6, okay. So when I do that, the answer comes out to be 2 into 2 4, okay, and 10 raised to 8 comes outside, okay, 10 raised to 8 comes outside, okay. I will take that uncommon factor inside the matrix. I will keep common factor outside the matrix. So 4 minus 4 minus 4 4 multiplied by the displacement vector. Okay, now rho AL by 6. Okay, rho AL by 6 happens to be 0.67. Okay, so 2 times of 0.67 is 1.33. So I have 1.33, 0.67, 0.67, 1.33. Remember, omega square is common for all. So omega square stays outside. Multiplied by the displacement vector matrix. Okay, now this is what I am getting for one element. Okay, this is what I am getting for one element. Okay, and the same value I will get for the second element. Okay, the same value I will get for the second element, because for second element also I will write the element matrix equation. For second element, what I will do? Okay, I will write here U2, U3. Okay, I will write here U2, U3. The values are gonna remain same. Okay, the values are gonna remain same. Okay, so why values will remain same? Because there are no changes. Okay, since they have asked us to take length as 1 meter. Okay, length as 1 meter. So if we are going to divide it into two elements, okay, the individual element length will come as 500. As come as 0.5 meters. Okay, 0.5 meters. Okay, so this length is 0.5 meters, this length is 0.5 meters. Okay, and since I have both the lengths as same, okay, both the lengths as same, so I have all other factors also same. So cross section area is not changing, Young's modulus is same. Okay, so my AE by L value will remain same, even my rho AL by 6 value will also remain same. So that leads the even second matrix equation, element matrix equation, will also be exactly same. Only the change will be the displacement values. Now the displacement values are U2 and U3. Okay, U2 and U3. Okay, remember I just said L is 1 meter in earlier EME. L is not 1 meter, L is 1 meter divided by 2. So that is 0.5 meters. Okay, 0.5 meters. So that is how we need to do this. Then I have, since both those equations, okay, which are exactly same, I can easily compile an element global matrix equation. Okay, element global matrix equation, or only global matrix equation. So 10 raised to 8 stays outside. 4 minus 4 minus 4. Then here 4 plus 4 will come. Okay, 4 plus 4 will come. So again minus 4 minus 4 4, and these two places will remain as 0. I have U1, U2, U3 as the displacement vector matrix, is equal to omega square, common factor stays outside. Okay, inside the matrix 1.33, 0.67, 0.67, 1.33 plus 1.33. So that makes 2.66. Again 0.67, 0.67, 1.33. Okay, multiplied by U1, U2, U3. Okay, multiplied by U1, U2, U3. Okay, now I know that the boundary condition, okay, U1 is equal to 0. Okay, U1 equal to 0. So what I can do, I can apply the Gauss elimination. Okay, Gauss elimination I can apply and get rid of the first row and first column. Okay, get rid of the first row and first column. So then that leads the 10 raised to 8 as the common factor. So 8 minus 4 minus 4 4. Okay, 8 minus 4 minus 4 4. 10 raised to 8 is the common factor. U2 U3, U2 U3. Okay, on the right hand side I have omega square stays outside. 2.66, 0.67, 0.67, 1.33. So that's what I have written over here. 2.66, 0.67, 0.67, 1.33 multiplied by U2 and U3. Okay, now what we need to do is, okay, we'll bring everything on one side. Okay, we'll bring everything on one side. So we'll bring this on the left hand side and equate everything to 0. So what I will have in turn is 8 into 10 raised to 8 minus 2.66 omega square. Then minus 4 10 raised to 8 minus 0.67 omega square. Then minus 4 10 raised to 8 minus 0.67 omega square. And 4 into 10 raised to 8 minus 1.33 omega square. Okay, and the displacement vector matrix is going to be common now, U2, U3 equal to 0. Okay, now in this particular matrix equation, it is the matrix equation of the order some square matrix 2 by 2 A multiplied by a column matrix U is equal to 0. Okay, AU equal to 0. So if we want to find out the non-trivial solution, okay, of the matrix equation, okay, non-trivial solution, when we try to find out the non-trivial solution, okay, when inside the matrix if we have some unknown term, okay, if inside the matrix we have some unknown term and we want to find out that unknown term, then we will go for a non-trivial solution. Okay, non-trivial solution means the solution which can be found out. Okay, and if we need to do that, okay, then the determinant of this matrix we should equate to 0 in order to find the unknown term. Okay, in order to find the unknown term. So that's what I am writing. A matrix A, which is a square matrix multiplied by a vector column matrix, is equal to 0. And if my square matrix A is having any unknown term, okay, any unknown term, okay, then I will find the determinant of A and equate it to 0 to find the unknown term. So that's what I am doing. Determinant of A equal to 0. So what I will do, 8 into 10 raised to 8 minus 2.66 omega square minus 4 10 raised to 8 minus 0.67 omega square minus 4 10 raised to 8 minus 0.67 omega square and 4 10 raised to 8 minus 1.33 omega square. Determinant, okay, of the entire matrix equal to 0. So what is the determinant? The cross multiplication, okay, this multiplied by this minus this multiplied by this equal to 0. That's what I have to write. So that is what I have written over here. 8 into 10 raised to 8 minus 2.66 omega square multiplied by 4 into 10 raised to 8 minus 1.33 omega square minus, okay, remember these two terms, okay, these two are same terms, so I can even combine them and write the whole square. So that's what I have done over here. Inside bracket minus 4 10 raised to 8 minus 0.67 omega square, the whole square, okay, the whole square equal to 0. Okay, now how you can solve this? Okay, how you can solve this? You can just simplify first. Okay, you can just simplify first. So just open the brackets. Okay, open the brackets, do the multiplications. Okay, and open the brackets. So it will go like this. Okay, here you have 8 4s are 32. 32 into 10 raised to 8 minus, okay, 4 4s are 16. Okay, 4 4s are 16. So 32 minus 16, that is 16 10 raised to 16. Okay, 16 10 raised to 16. Okay, this 8 10 raised to 8 multiplied by 4 10 raised to 8 will eventually give us 32 10 raised to 16. Okay, and here minus 4 10 raised to 8 the whole square will give us 16 10 raised to 16. Okay, and that 32 minus 16 will be 16 10 raised to 16, which will be a positive number. So that comes first over here. Okay, that first comes over here. Okay, then similarly we do this 2.66 minus 2.66 omega square multiplied by 4 10 raised to 8 minus 1.33 omega square multiplied by 8 10 raised to 8. Okay, when we add subtract them, okay, with this minus 0.67, 2 into minus 0.67 into minus 4 omega square, okay, we eventually get as 26.68 into 10 raised to 8 omega square, and that will remain as minus. And at the last I have this 2.66 omega square multiplied by 1.33 omega square, okay, minus 0.67 omega square. Okay, so I will have a term with omega raised to 4. Okay, I will have a term with omega raised to 4. So that eventually comes out to be 3.1 omega raised to 4. Okay, 3.1 omega raised to 4. So now I have this equation. Okay, I have this equation which I can say is a if I try to find the solution of this. So what I will do is I will first treat this as a quadratic equation of omega square. Okay, quadratic equation of omega square. Okay, so I can solve this in calculator directly. Okay, I can solve this in calculator directly. Okay, with a matrix of or the equation of 3 unknowns. Okay, equation of 3 unknowns, or the equation with degree 2. Okay, equation with degree 2. So I will have here I can put these coefficients, okay, 3.1 minus 26.68 and 16 into 10 raised to 16, okay, of course with 10 raised to 8 over here as well, and get the answer. The answer will eventually be the answer in terms of omega square. Okay, the answer will be eventually in terms of omega square. So that's what I have written over here. Omega square is equal to 7957875117.7 and 64857643. Okay, so the answer is not complete over here. We need to find omega. Okay, we need to find omega, which is natural frequency. So see, remember, we will have 4 values actually. Okay, we will have 4 values. Okay, but we will be only keeping those values which are positive. Okay, we will be only keeping those values which are positive. So these are those 2 positive values. Remaining 2 values which are not positive, okay, we have not included them. Okay, we have not included them. And from here also we will have 2 values. Okay, so the negative value we are not going to consider. Okay, the negative value we are not going to consider. So, and from here also we will have 2 values. The negative value we are not going to consider. So omega eventually comes up to be 28,209.7 radians per second, and from this value we get 8053.42 radians per second. So remember, we started with this EME, okay, which had a mass term, okay, and we said that the mass term that we are going to solve this problem with is a consistent mass if nothing is mentioned. Okay, if nothing is mentioned. Now a change. Okay, what is the other type of problem asked in the exam? The other type of problem asked in the exam is where they ask you to solve by lumped mass matrix as well. Okay, so lumped mass matrix as well. So this is the answer which we got by consistent mass matrix. Okay, it is also possible that they may ask another part of a question where they also ask you to solve the natural frequency solution using lumped mass matrix. So what is the change that you are going to do? Okay, the only change that you will be doing in this is you will be using a lumped mass matrix equation. So lumped mass matrix equation goes like this. You will only have diagonal term in your mass matrix. Okay, you will only have diagonal term in your mass matrix, and that diagonal terms value is going to be rho AL by 6. Okay, rho AL by 6. Okay, the remaining things are going to remain as it is, and you will be solving them. Okay, you will be solving them by taking this as the mass matrix. Okay, again we will be doing the non-trivial solution. Again we will be finding the determinant of that square matrix. Again we'll have an equation in omega raised to 4, which will be omega square quadratic equation. Okay, again we will find 2 values of omega, and that is how we need to approach. Okay, they may also ask you to find and compare it with the exact method. So for exact method also we know from DOM how to find the natural frequency by exact method. It is directly found out by formula. Okay, so you can also put the third condition. It is the exact method for finding the natural frequency. They sometimes specify the formula, or that formula is not that difficult to remember as well. It is, I guess, under root E by rho. Okay, under root E by rho, 1 upon 2 pi under root E by rho. That is what the formula is. Okay, so with that formula also you can find out the natural frequency directly. Okay, so likewise they may ask you to compare the frequencies which you are finding with the exact method, or they may also ask you to compare the frequencies with consistent mass matrix method and lumped mass matrix method. So these are the variations of problems that are consistently being asked in the exams. Okay, so I have just covered one type, which is with consistent mass matrix, and we've just discussed the different types, which are the lumped mass matrix. I just told you. Okay, the process remains exactly same. Okay, and the third one is with the use of the formula, which is we call as the exact method. Okay, which is we call as the exact method. So these are the 3 type of variations in the vibration analysis problems are asked in the exam. Okay, and as far as these problems are concerned, all are one-dimensional problems. Okay, we will not be going into 2 dimensions. Even they don't ask the transverse vibration problems. Okay, so we will in next lecture see one transverse vibration problem just for the understanding. Okay, and then the 6th module will also be over. So this is as far as the natural frequency or of the axial rod. Okay, axial rod is concerned, and we found out the 2 values of natural frequencies.